When we're dealing with solutions, we can start with a really concentrated solution, but usually that's not super helpful to us. In fact, if you're working in a lab, usually you are getting your materials in really, really concentrated solutions that we would call a stock. And then we would go about the process of diluting. And when we dilute in chemistry, there's a really important rule, and that is that the number of moles doesn't actually change. You see, the moles stay constant in a solution before and after we dilute. And that's one of the huge keys to the way that we work with a dilution. So to give you a quick example, imagine having a flask that, let's say, has 1 liter of water, and let's just pretend each of these is a mole. Well, that's the equivalent of having about 6 moles per liter, or 6 molarity. If we were to dilute this, and basically all we're going to do is add water. So that means we're adding more solvent, and let's pretend now we're up to 2 liters. Well, the number of moles is still 6. The number of moles has not changed, but the overall volume has. What that means is the moles before and the moles after dilution are exactly the same. This leads us to an important equation that we use in chemistry. You see, if the moles at the beginning are equal to the moles at the end, we can actually set that up as an equation. What we can then do is use the idea of molarity. Since molarity is the moles per liter, we can rearrange this equation to say that the moles are the molarity times the liters. Now, instead of writing moles right here, what I can actually do is just substitute in molarity times liters. So what that means is the molarity at the beginning multiplied by the liters at the beginning should actually be equal to the molarity at the end multiplied by the liters at the end. And the way this equation works, it actually doesn't matter our units for liters or for volume. So a lot of the times we will abbreviate this as M1 V1, where V is volume. And so that volume can be in either milliliters or liters, is going to be equal to the molarity after diluting multiplied by the volume after diluting. This is what we call the dilution equation. It is meant only to be used when diluting, when to take a high concentration, add more water, and make a lower concentration. So now that we've seen this equation, let's take a look at how we would use this equation to do a calculation. So let's say we had 53.4 milliliters of a 1.50 molarity solution of sodium chloride, but we need 0.8 molarity solution, so we want to know how much can we actually make. So here's what we want to do. As we work through this problem, I think the best thing to do to start is to organize it. So that means find out what is M1, what is V1, what is M2, what is V2 before we even start putting things in an equation. So reading the information, we have a 1.50 molarity solution, but we need it to be 0.80 molarity. So that means 1.50 molarity is my number 1, M1, my starting concentration. And 0.800, well, that's what I want to get it to. That's my M2, my final concentration. The beginning concentration is 53.4 milliliters. So 53.4 milliliters. And it's actually asking us how much can we make? So what's our final volume going to be? So I like to do this, and I think this is an important step in any problem solving, is sort your information and organize your thoughts before you jump in. So now that we know that, we can use our equation M1 V1 equals M2 V2. And when we rearrange this to solve for V2, what we're going to be doing is dividing by M2 on both sides. M2 is going to cancel. And I just need to move my equal sign. So what we're going to get is V2 is equal to M1 V1 divided by M2. Now, I'm going to move this around because I always like, it's just like a particular habit of mine. I like to make sure that I am working on the same side. I also have another particular habit. I always like to keep my equal signs in a line. So V2 is going to be M1 V1 divided by M2. So now that we've rearranged our equation, let's plug all our numbers in it. So M1 is 1.50 molarity. And I do find it helpful to actually write your units in case you make a mistake. You can find your mistake more easily. V1 is 53.4 milliliters. Now, with this equation, it actually doesn't matter what units you use. And I'm going to show you that over on the side here in a moment. We're going to divide that by M2, 0.800 molarity. That means that V2 comes out to be 100 milliliters. Now, I'm going to put this little dot to show that I needed 3 sig figs, to show that these are all significant. If you really wanted to, you could write this in scientific notation to say 1.00 multiplied by 10 to the power of 2 milliliters. Now, one thing I mentioned is it actually doesn't matter what units you use. What does matter is you make sure that volume units are the same. So if I were to change this into liters, this would be 0.0534 liters. So if I were to redo my equation over on the side here and go 1.50 molarity multiplied by 0.0534 liters, it's a liter by the way, divided by 0.800 molarity, what I would find is that my answer is 0.100 liters. You see, molarity divided by molarity, that goes away, and the only units you have left are whatever units you chose for volume. And 0.100 liters is exactly the same thing as 100 milliliters. So it doesn't really matter what units you use, but it does matter that if you have more than one of the same unit, they have to be the same. So I have 2 molarities. If I were doing this and I had 2 volumes, I'd have to make sure they were both milliliters or both liters. But in the dilution equation, it doesn't matter if you use milliliters or liters, as long as you're using the same thing on both sides of the equation. So now that we've done that, let's take a look at a second example. So this is our next example. 100.0 milliliters of 2.5 molarity potassium bromide solution is on hand. You need 0.5500 molarity. What is going to be the final volume of the solution that results? Okay, so in order to solve this, let's do this the exact same way. Let's sort our information. So 100.0 milliliters of 2.500 molarity KBr solution is on hand. Well, that's going to be M1. 100.0 milliliters of 2.500 molarity solution. And we want to make it 0.5500 molarity. What is the final volume that results? Well, we're solving for the same thing. We're solving for V2. And I know I rearranged last time. I'm not going to rearrange this time because we did the exact same thing. So now we're just going to plug our values in. So M1, 2.500 molarity. V1, 100.0 milliliters. Since I'm using milliliters, my answer is going to be in milliliters. Divided by 0.5500 molarity. Punch this in your calculator, and what we're going to find is that we get 454.5 milliliters. Remember, we're working in milliliters because we left this unit in milliliters and molarity cancels. So there you go. This is how we use the dilution equation. And I think at this point it's important to recognize that we only use the dilution equation for dilutions. So if you see the word dilution, watered down, added solvent to, those are all indicators that you're dealing with some kind of dilution. Do not use the dilution equation for stoichiometry problems or anything else. But hopefully this helps you see how you can use it, and thanks for watching.